上海的朋友们，你们好。我叫大伟 and unfortunately I don't speak Mandarin yet, but I'm very excited to be in this amazing city and talking to an amazing audience as well. Today's session is called Two Engineers, a Billion Users, and AI Agents. So previous slide, sorry. So for a bit of context, my name is David. I work as a staff software and machine learning engineer at Treasure Data based in Tokyo in Japan. I also happen to be a Google developer expert in ML and AI, and I also work as a contractor for the Keras team in bringing foundational models to the Keras platform, as well as the core library contributions. The place that before that one, I've worked as a software engineer as well as a machine learning research engineer, so I've kind of been in both of those roles and love switching between them. One thing I've noticed between those two groups is that oftentimes information is not really being shared, and a lot of the common knowledge between the two groups doesn't really stand. So in the presentation, I'd also have to let you have a bit closer.
Would you change the mic?
Yes.
Yeah, sorry.
No problem, thank you. That's much better. So within the presentation, I would like to have some lessons oriented more towards the software engineers and some lessons oriented more towards the MLEs. So I'm hoping that those, especially those that are trying to do both at the same time, might benefit the most. So a little bit about Treasure Data. Treasure Data is a customer data platform. We work on breaking down the silos between various different data sources, unifying customer data into a single foundational platform, and allowing our customers to draw intelligent conclusions based on that data. Some of these include, for example, orchestrating your customer journeys, figuring out best ways to engage your user base, as well as, in this case, machine learning, which is where I come in. We operate at a pretty large scale, so we manage about 50% of the connected user internet's profile. Sorry, the internet connected users' profiles. So for us, scale is a very, very important topic, and being able to cover the entirety of our user base is a common concern. We've recently developed and deployed a lean machine learning platform, which is specifically meant to scale for enterprise use cases. And in this presentation, I specifically want to focus on the 5 months it took us from design to production for that system, but perhaps even more importantly, on the 5 months of lessons we've drawn while developing and deploying the system. So, whoops, previous one. Before we go into the lessons, the first question we really need to ask is why this is really a relevant topic for us today. And the industry has figured out how to scale software a long time ago, so kind of what's up with machine learning and why is that really a topic we want to discuss in 2025? Why are the ML models any different from standard software? To answer that question, it's very useful to take a 1-minute detour just to get into the kind of foundation of why we use these models in the first place, and then we can get to the lessons. Fundamentally, models are universal function approximators. What this means is that if you know a function, or even better yet, if you don't know a given function, you can approximate it using an ML model. And why the functions are very important for us is explained very well with the person here. If we can play the video now, that would be great. Takes a second. Apologies for the wait. If not, I can maybe recreate the video by myself. So, the reason why we care about functions is that functions describe the world. So my voice going into this microphone is getting mapped using a function. It gets mapped onto the speaker, into your ears. Everything that happens around us can be modeled by functions. Different aspects of mathematics study different forms of functions, And the functions describe the world as we know it and as we see it. In more practical terms, doesn't seem to want to go to the next slide. Went there, yes. So, for example, if you have a function such as a partial differential equation, in this case the Navier-Stokes equation, the solution to that function describes how fluids and gases move in closed systems. This function specifically has found various use cases in engineering and science and has been applied in many different fields. This solution can be approximated using an ML model, where you don't have the computational resources to really solve the function from time to time, for different time steps. You can use an ML model to approximate it. Or in a more palpable example, if you can formulate a user's behavioral policy using a function and then define a production policy for a different model, you have yourself effectively a banded solution. And parts of these can be approximated, again, using functions. What that means in practice is that when you go to your favorite marketplace, you get recommended a good book that you really like. This way? Oh, that works. Beautiful. Okay, so what's really difficult about just running those functions? Generally speaking, it's really not. You just call model.predict, and you might need a lot of memory or some time for that to execute. But also it might explode. So let's do a simple case study, something that recently happened in my workplace. We deployed a solution using a production-ready library onto the cloud. And this was, again, a production-ready library written by a team that has shipped a lot of software before. And then one Saturday night, very near midnight actually, my phone started ringing. I was pinged for an anomalous metric on our dashboard. And if you take a bit of a closer look at the dashboard, our disk usage went from 0% to 98% in the span of a single minute. We were waiting for the instance to crash. There's no way for us to recover this run, so we were expecting customer escalation to come in any minute. What happened next is that it actually recovered, went back to 0%. So we thought, well, maybe this is a metric bug, maybe this is something else. This probably didn't actually just happen, right? Turns out it very much did happen. And after digging through the code for some time, we figured out what the actual cause was. One of the authors of the library thought it would be a practical step and a very convenient step to offload a lot of the memories from a lot of the objects from memory onto the disk as effectively a temporary cache. Now, because the library does encourage you to use very large RAM sizes in the hundreds of gigabytes, this effectively means that one of the basic assumptions of the library is that you can store hundreds and hundreds of gigabytes onto the disk at will. Now, while this is probably a very convenient assumption for the author of the library, if you put in a software engineer or a software reliability engineer into the mix, they probably would have gotten a heart attack by seeing that. So this gap is what makes production ML very difficult. That being said, I want to welcome you to the lessons we've learned while building this platform. The first lesson was that ML libraries are still very much research-oriented, and you will have to assume that you will have to do a lot of unplanned work to patch these libraries. So even when they're tagged as production-ready, oftentimes the reality is they're not really production-ready. Oftentimes, ML software breaks at scale, has underlying assumptions which are just very unusual for production software, or just straight up prevent scalability. In practice, we oftentimes need to customize our ML tooling. So besides architecting a scalable system, which is already well known, both within the ML sphere and the software sphere, you also have to do a lot of unplanned work, such as in our case, we had to rewrite CUDA kernels, change internal data types. We had to hack around which versions of things we were using and then inject a different version onto other dependencies to make sure that they still run. And we also had to drill down into the implementations, switch between CPU and GPU implementations, and make sure that we can dynamically switch between devices we are running on. These are oftentimes very deep, long sessions of jumping between code bases, reading implementations, reading the original research papers. And this also becomes very difficult to convey to stakeholders. Oftentimes, it's very difficult to explain to your PM why you're spending the extra time trying to figure this one out. One specific case that we've recently had is one of the libraries that we were using had a hard constraint on CUDA 11, but the hardware we were using was running on CUDA 12. This is a trivial thing to change. You can just change the version, but a different library that we were using had a hard constraint on CUDA 12. So we were kind of in a deadlock as to which one we can patch. It turns out it was easier to patch the one that's hard constraint to CUDA 11. What we ended up doing is hacking the runtime such that the library thinks that it's running on CUDA 11, but actually runs on CUDA 12. Besides that, we also had to rewrite a couple of CUDA kernels. It had an index that was encoded in an integer 32, which means that we could only go up to about 2 billion indices, which was not really the scale that we wanted to go to, and some other steps. But all of these ad hoc changes and fixes to the library actually allowed us to bring down the inference time by over 80%, and also keep our costs down by over 40% per profile. This was obviously work that you cannot plan up ahead of time, but it does pay off to put in the work. So in practice, enterprise ML oftentimes means identifying assumptions within the libraries, working around them, or patching them in different ways. This makes it obviously very easy to introduce tech debt. It becomes very easy to trap yourself in an endless spiral of trying to patch and patch and patch. And finding the right balance here is really, really crucial. There's no one single rule that you can follow to find this balance. Lesson 2 is about leveraging software architecture knowledge. So software engineers have been trying to figure out software design for decades, and you can leverage this knowledge. So given any sort of problem that you're working on, this is usually going to be a very specific domain problem that you're working within a certain company. You can oftentimes kind of stop and think about whether this is a problem that already exists somewhere in the industry, maybe in a different form, maybe with a different name, but you can usually find one. If you can identify the class of the problem, or formalize a problem as an instance of another already studied problem, you can both leverage the conceptual tools that people have built before to solve this problem, but also oftentimes the theoretical backing of those conceptual tools. So for example, you might notice that your problem is being solved by multiple different patterns that have been studied for a long time. But for example, pattern 1 has a structure that doesn't really make it very simple to make a pricing plan for your sales team. You can have multiple competing architectural proposals, trying to find the right trade-offs between all of these options, and then go for the one that works best for your organization. In our case, this is actually our internal system design diagram for the platform that we have built. And it's really simple. Simple does it most of the time. We've identified our problem as being a problem of workload distribution, but specifically workload distribution that has to be aware of both the resources of the compute environment it's running in, but also the resource requirements of the solutions we're running on that compute environment. So we've fundamentally adapted a sort of MapReduce pattern onto our specific machine learning problem. And MapReduce has been used a lot in various different software all around the globe. It's well studied, it's well known, it's very simple, and it's highly effective. Stay simple and try time-tested strategies. So for our specific case, once a machine learning run request comes in, we very simply decompose it into a set of different jobs, which run in parallel and independently one from another. We map them onto a whole table that we can then orchestrate. We track their state, both internally and externally, and then we map the results onto the output tables. Some of these jobs run on CPUs, some of them run on GPUs. We might even support a hybrid solution as well. But this is fundamentally a very, very simple architecture that does the job for us as well. So lesson 3 is very obvious. So this is kind of like when a doctor tells you to sleep well or eat well or exercise. but engineering discipline pays off, and it pays off very fast. This is also a screenshot of one of our internal documents that we've decided, that we've written very early on in the process. And if you can take a look, it has two very, very simple core design principles. One of them is to keep simplicity and flexibility, and the other one is to keep maintainability. These are very obvious. You want to have this in basically every piece of software everywhere. The one thing that's very common for ML development is that these things kind of get lost in the process very quickly, because ML is kind of like a special case in a lot of software, and these principles just kind of fade through time. We've specifically written these down, even though they're very obvious, because every time we had a point that we wanted to bring, every time we had a disagreement, or we were considering something new, we could evaluate that proposal through the lens of these two principles. That really helped us a lot. Finally, we also had, for example, the 2-minute build pipelines. Even though the metric might sound impressive, the metric itself doesn't really mean much. You have to think about what the metrics mean to you. In our case, what this meant was that between the time that we press enter on a commit message to the time that somebody in our team can actually use the solution in a shared development environment, either to prove a point or to share a point across, it took almost 2 minutes. This enabled rapid iterations. So lesson 3 is effectively to have the discipline to commit to engineering excellence. Lesson 4 is, I think, one of the most important ones that we've had in the few months that we've been building this. Anything new causes skepticism, and transparency builds trust. Oftentimes, the blockers are not really technical. It's when your PM doesn't quite understand why you're proposing something. It's when your team doesn't quite buy into the architecture that you're trying to propose as well. And these difficulties oftentimes don't arise because of a fundamental distrust of you. It's about a fundamental misunderstanding of how your work is playing out. ML development is oftentimes very difficult to convey. A lot of these reasons are not technical again as well, but as long as your team doesn't trust what you're doing, it's very difficult to get your point across. One of the first things we did was to formalize a structure in which we can share knowledge and in-progress lab reports. So on the right, I did have to remove the names of the lab reports and the people, but we have a public table of everything that we've done while testing this system out. We've made sure to have that liberally linked to in various different documents. It's also in one of our main pages, next to the technical decision logbook as well, and our user feedback logbook. And we made sure to very liberally share this with all the people in our company. Initially, even though it was public, this was primarily being used by engineers. But as more time passed, we started seeing salespeople coming in. We started seeing PMs come in. They've left comments, they've asked clarifying questions. And after some time, we've also seen them being shared in different places. And we've seen these links end up in basically every document in the company later. So it really, really helps demystify what's going on and to drive a lot of the technical buy-in within your team and outside of the team. One thing we found that really, really helps in this is to have a good template. This keeps your documentation consistent, so people that read your documentation know what to expect, but it also makes it easy for your teammates to contribute to the documentation. You open up the template every time you write something, you know how it looks like, and it helps you write a good document. But don't go for generic templates. Don't just go onto a search engine, find a template and copy paste it. Don't have ChatGPT write it for you. These templates have to be highly specific for your organization. Try to figure out the signal you want to amplify within your organization, what people care about. Talk to your sales teams, talk to your GTM teams. Figure out what's important for them and tailor your templates such as to answer the questions they might have. Lesson 5 is about testing. So you want to test, test, and test. Things oftentimes break at scale in ways you can't imagine, and you have to test them individually. And besides testing them individually, you also have to test them end to end. Any single component can become a bottleneck. And oftentimes these predict in very unpredictable ways when you scale them up. So for example, we've talked about the MapReduce pattern previously. Conceptually, this solved the problem, but we weren't really sure whether that pans out in practice. On the bottom left, we've been testing our implementations against old implementations and realized that we have a differential of about 50 times in the speed of execution. But we also tested our infrastructure providers to make sure that AWS can provide us with the resources that we need. And then fundamentally, we've also tested our state synchronizer as well beyond what we actually really need. So on the bottom right, we have 350 runs running concurrently on a data volume of 12 billion profiles. We don't have that many people on the planet, so we can't run ever actually on 12 billion profiles, but knowing that we can go to that level gives us confidence to stick to components that to get us that performance. It really, really helps if you can define and design your components to be predictable. Our state synchronizer has been designed to be predictable. It scales linearly with the number of the runs that we have. So even though we've only tested up to 350 runs, and here on the left you can also see the collection of those runs, we can relatively easily extrapolate how that would look like if we ran a significantly higher benchmark. So on the plot on the right, we have an extrapolation of up to 2,000 runs. Knowing whether you can stress test and how you can, knowing whether you can trust your components allows you to have a lot of trust placed in them. One thing that's really important to remember is that you don't just run a test once, you continuously have to test these through time as well. Lesson 6 is about AI applied to enterprise. So within Treasure Data, we've formed a unit that we call the Engineering Dev AI unit. And some of the primary goals of that unit are to track usage of AI, the impact of that AI, as well as to shape policy around usage within the company. I currently work also as the technical advisor for that unit. So within the unit, we designed and conducted an experiment lasting 4 months on the impact of AI, and we were specifically using Cloud Code in this case, on our engineering productivity. And one thing that we've concluded from that report is you don't all become 10x engineers overnight, but we do have an average relative velocity increase of 30% across all of our repositories engineering teams. This might not sound like a lot, but for enterprise use cases, this is massive, especially because oftentimes for enterprise, the bottleneck is not really in writing the code, it's in everything that goes around that. And from here, we actually have a couple of lessons drawn from AI specifically. So lesson 7 is that AI is very much a double-edged sword. It holds a lot of promise, but it can very quickly burn you if you use it in the wrong way. We've noticed that as teams get more experienced in using AI, they benefit more from its usage as well. And one thing we've also noticed very commonly in our engineering teams is that initially there's a lot of excitement around the usage of AI and a lot of excitement in the initial stages of use, followed by a slow and gradual decline in expectations as people find more and more problems baked into the solutions that they've built. The second one is that review fatigue builds up very fast. One thing that CLI coding tools use is they show you every change, but these are oftentimes actually very difficult to track. So even though they technically show you the changes, you oftentimes have to conditionally accept something based on something that's going to come in the future, and keeping up with this context is very, very difficult. So we actually had a very funny case where the engineer that I was working with pointed something out. I've opened up a PR using an AI-assisted tool, and I've reviewed every single change that was suggested in the CLI. I felt like this was a good enough PR, and I opened it up confidently. What my colleague pointed out was that this was not my code. It didn't feel like my code. And he thought that I would request changes to this PR rather than approve it. The funny thing was, the very next day, he opened up a PR using an AI-assisted tool, and the gut feeling that I had was, this is not Aki's code. He would request changes for this PR as well, even though from his perspective, it looked good enough, and he felt like he reviewed it enough to open up the PR. It's very, very easy to develop blind spots during AI usage. So one thing that we found that really helps is you can switch hats. You can take a break, you can drink a coffee, maybe exercise a tiny bit, reset your own context. And if you open up, for example, a draft PR and review it as if it's someone else's work, I found that very commonly I find things that I haven't found before in the step-by-step usage. This is about my reaction in those cases. One of the final lessons that we have for AI is that they are still, as of today, and I hope this changes in the future, deeply misaligned with good engineering practices. So AI models tend to hide, silently fail, print very large messages about how things are working super well, and maximize user engagement rather than maximize the value delivered. This might be because they are trained to maximize user engagement, oftentimes in kind of chatbot form. And also they're trained for the wow factor, for perceived value rather than actual value. So in kind of fear of losing the user, they oftentimes go for quick paths to securing that we stay trusting in what they're proposing. And also, as most information online is kind of for illustrative purposes, and they come with a kind of a disclaimer of like, in production you use something proper. These are fundamentally baked into the models, even if you request them to do otherwise. And then the final lesson for today is AI is a great tool, but a bad master. One thing and one way I like to think about using these tools is kind of as a lossy decoder for your intent. So if you imagine your prompt as a very rich input vector that gets decoded by an LLM tool, it decodes your intent. And one thing that really, really helps is that if you can identify when that decoding process of your intent is not accurate. So if you cannot do this from scratch, if you cannot do a task from scratch, you probably won't have fun using AI because it's going to be very difficult to notice this gap when it does arise. And everyone knows that it does arise very commonly in usage. For us, this is kind of the differentiation between what people call currently work slop and something that's actually viable in production. So have the confidence to work on things on your own and use them to remove the physical bandwidth of typing out your ideas rather than having the ideas of an LLM. Thank you for the time. If we have some time left, maybe we can do a Q&A session as well.
Yeah, maybe we have some question time for the audience. 因为今天就是大卫的话也是从日本专程而来嘛，所以大家也可以问问看大家有没有什么想问这位就是我们Billiion工程师的这个问题，大家可以举手提问。如果有，就我们也可以用中文、用英文都是可以的。
Hello. Hi, David. First, thank you for your presenting. And I'm actually a software engineer at PayPal, and I have one question for you. So my manager always asks me, "Oh, hey, can you improve some system or something with AI? You build an agent or you use some workflow?" So one question I have is that, like for normal software engineers, is there something really we can do to improve some process with AI other than we have to use AI because the leaderships they want us to do something with AI? Is there like some real things we can improve the system with AI from your perspective? Thanks.
Yes, thank you. I think that's a very good practical question. I think that's probably going to be a question that a lot of people have in their daily work as well. So I'm generally skeptical of just applying an agent on top of things. However, I do think there's a way to apply agents in a way that really works well, especially within engineering organizations, which is to define the right tools that it can use. Whether that means you define your own tools or find tools online that are pre-approved or handwritten, AI agents are really, really good at connecting the dots. If you use them as glue to connect different processes that you define, they can do really wonders. But if you just apply an AI agent on top of textual data or unstructured data, they oftentimes veer off course into something that doesn't quite really work for very domain-specific applications. So one thing that I would advise, if you're looking to optimize a process, for example, is to define individual fine-grained steps and tools for an AI to use that are pre-approved, that you can just automate using glue code, which is essentially made by the AI itself. Does that make sense? Thank you.
Thank you. 谢谢这位嘉宾。The next person. 再抽一位。
Yeah, thank you very much, David. My name is Jessie. I'm working in a manufacturing hardware company. So I currently want to build up like an AI machine learning capability in my company, and then build up like a group. So like from your experience, how many people like should I should leverage or hire for if I want to bring up AI machine learning group for our hardware? You know, like currently hardware using like YOLO is good enough, but like I just want to know like how many people may I need to like leverage, and also like what are their responsibilities, because it's completely new and everyone wants to jump in.
Yes, thank you for the question. I think that really depends on the company they work in, so I think it's very difficult to give a specific number as an answer. In our case, we built this platform with 2 engineers. So that's a very, yes, 2. That's part of the title as well. But that's a very uncommon case. I think if you're working within manufacturing, especially if you work very closely with hardware, a lot of people in the sphere don't have experience working with hardware. I think it's a very, very exciting combination of AI with hardware, and I think China is probably one of the best places for that sort of sphere to work at. But as far as I can tell, at least from my experience, it's not a very common experience for people to have. So I would expect that you might struggle finding people in the beginning, and might need a slightly larger team, at least kind of in the initial stages, to define your processes, to find good practices for your specific organization. But I cannot give an exact number. It's just really, really depending on the company specifically. But good luck.
Thank you.